Hello everyone. In today's lesson we're going to talk about bond length and bond strength with respect to covalent bonds. So let's first start with a definition for bond length. When we describe the bond length of a covalent bond, we're talking about the distance between the nuclei that are bonded at the point of maximum net attraction. So we've talked previously in class about how when bonds are formed, repulsive forces are minimized between atoms, and attractive forces are maximized, or not necessarily maximized, but the net attraction is maximized. So we're arranging the atoms in such a way that when we cancel the repulsive forces out from the attractive forces, we end up with a maximum net attraction between the two atoms. And this is going to result in a minimum potential energy, electrical potential energy between those atoms as well. And so at this point of maximum net attraction, if we were to look at the distance between the bonded nuclei, this is what we would describe as the bond length. And typically we measure these distances in a unit called an angstrom. So I have a couple of examples over here, two diatomic molecules, fluorine, which is singly bonded diatomic molecule, and nitrogen, which is a triply bonded diatomic molecule. And we've got the bond lengths indicated for both of these molecules here as well. And notice that they're measured in this unit called an angstrom. So we see for fluorine that the distance, the bond length at the point of maximum net attraction is 1.43 angstroms, and for nitrogen it's 1.10 angstroms. So just for a little bit of context, what exactly is an angstrom? Well, it's equal to 1 times 10 to the negative 10th meters. So it is a very small unit of measurement. And again, we see with these molecules, fluorine and nitrogen here, that it's roughly on the scale of an atom. So it's a convenient unit of measurement for us to use when we are looking at bond lengths, as we will be in today's lesson. So a couple of other points about bond lengths that we should be familiar with before we go too much farther with our discussion here. First of all, multiple bonds tend to be shorter than single bonds, and we see that with the bond lengths that we have for diatomic nitrogen and fluorine over on the right side of the screen. So multiple bonds tend to be shorter than single bonds. And of course, there are always exceptions to these generalizations, but if we were to compare a single bond versus a double bond versus a triple bond, it would be reasonable for us to conclude that the triple bond would be the shortest of those three bonds, and the single bond would be the longest of those three bonds. And this is significant because of the second generalization about bond length. We see that there's an inverse relationship between bond length and bond strength. So bond length and bond strength are inversely related. So this means that shorter bonds tend to be stronger bonds. Inverse relationship between bond length and bond strength. So looking at the two molecules that we have over here on the right side of the screen, fluorine with a bond length of 1.43 angstroms and nitrogen with a bond length of 1.10 angstroms, the shorter bond is going to be the stronger bond. So over here with nitrogen, because this is a shorter bond, we can conclude it will also be a stronger bond. Shorter bonds, stronger bonds, inverse relationship between bond length and bond strength. So as a general statement, multiple bonds tend to be stronger than single bonds due to this inverse relationship between bond length and bond strength. Now, if we want to quantify this bond strength, we're going to look at what we call bond dissociation energy. So bond dissociation energy is sort of loosely defined as the amount of energy needed to break a particular bond. So if we're going to look at this fluorine-fluorine bond in the diatomic fluorine molecule, and we want to, break that bond, and I say break, I've got it here in quotes. We're not really breaking anything per se, but we are getting rid of that chemical interaction, that electrostatic interaction between the atoms that holds the atoms together at a point of minimum potential energy. So we're separating those atoms from each other to the point where they are no longer chemically connected to one another. And bond dissociation energy is always going to be an endothermic value. It's going to take a net input of energy in order to overcome that attraction between those atoms that are covalently bonded. And as a result, these bond dissociation energies are always going to be given as positive values. So for instance, for diatomic fluorine, it's about 159 kilojoules per mole. That would be the amount of energy that we would need to input in order to separate or break 1 mole of fluorine-fluorine bonds. More generally, we define bond energy as the average of bond dissociation energies for a particular molecule. So what this means is if we're looking at a molecule with multiple bonds like methane, where we have a carbon bonded to 4 hydrogens, so 4 carbon-hydrogen bonds, if we were going to break all 4 of these bonds, it's not going to take the same amount of energy to break each one. And this is going to be due to a variety of factors, mainly the differing electrostatic attraction and repulsion as we remove atoms from the molecule. But the point is that each one is going to require a slightly different amount of bond dissociation energy. So when we define the bond energy for this CH bond in methane, it would be the average of each of those 4 bond dissociation energies. So this is a little bit more useful to us. It's a little bit more general than the bond dissociation energy. So we'll kind of use the terms interchangeably for the most part, but it's worth knowing that there is a difference, even though it might be a small one for the purposes of our discussion. At any rate, we see that bond energies are positive, as I said before, and we do see, consistent with what we discussed previously, that shorter bonds are going to have higher bond energies. So in comparing our diatomic fluorine and diatomic nitrogen molecules, the fluorine is singly bonded, and if you remember from the previous slide, we had a bond length of 1.43 angstroms, if I remember right. Let's go back and double check, just to be sure I'm not making that up. Yeah, 1.43, that looks good. And then we had a bond length of 1.10 angstrom for the nitrogen molecule. So shorter bonds have greater bond energies, and that is reflected with the bond energies of the diatomic fluorine and diatomic nitrogen molecules. We see 159 kilojoules per mole for fluorine, but 945 kilojoules per mole for nitrogen. So shorter bonds have greater bond energies. So what does this mean then in the context of chemical reactions? Well, let's take a look at an example. So here we have a chemical reaction between diatomic nitrogen and hydrogen gases to form ammonia gas. So this is part of what we call the Haber-Bosch process. What we're interested in here is in the course of this chemical reaction proceeding from reactants to products, we're going to have to break bonds for the reactants. So over here with diatomic nitrogen and diatomic hydrogen, we're going to need to break these bonds in order to form ammonia. And when we're forming ammonia over here on the product side of our chemical reaction, we're going to need to form bonds. We're making bonds over here on the right side. And so in terms of bond energies, breaking bonds, as we saw earlier, this is an endothermic process. So when you break a chemical bond, you're going to have to input energy. Energy is going to be consumed in that process. On the other hand, when bonds are formed, energy is released. This is an exothermic process. In bringing the atoms together to form a chemical bond, you're lowering the electrical potential energy of the system of atoms, and that difference in energy is given off to the surroundings in this case. So this is an exothermic process. Energy flows out of the system. So what we're interested in then is the overall either endothermicity or exothermicity of this process. So if we look at the entire chemical reaction from start to finish, are we going to have a net input of energy or a net output of energy? And so what actually happens here with this particular chemical reaction is that more energy is released when the bonds in NH3 are formed than is consumed when we break the bonds of the reactants. So since there is a greater amount of energy released when the bonds of ammonia are formed, overall this reaction is classified as exothermic. So we will have to have a net input of energy in order to break the bonds of the reactions, but break the bond of the reactants. And it wouldn't be a net input, I'm sorry. We're going to have an initial input of energy in order to break the bonds of the reactants. But then when we form the bonds in our product, there's going to be a greater amount of energy released. So if we look at the amount of energy that is input and the amount of energy that is output, there's a greater amount of energy output. So the balance makes the reaction exothermic. The balance is a net flow of energy out of this reaction system. So just real quick to finish up, we see that in an exothermic reaction, which again, that's what we had here with our example. In an exothermic reaction, let's highlight that, more energy is released when the products are formed than is consumed in breaking the bonds of the reactants. On the other hand, the reverse can be true as well. Let's undo that. There we go. I want a highlighter. There we go. On the other hand, in an endothermic reaction, we're going to see more energy consumed in breaking the bonds of the reactants than is released when the products are formed. So there would be a net input of energy in an endothermic reaction. So what we can do then is look at bond energies for reactants versus products in a chemical reaction. And these can typically be found in one of the indices in your textbook, for instance, or you can look them up online. But we can look at these bond energies and we can classify a reaction as either exothermic or endothermic based on the bond energies, whether the bond energies of the reactants or the products are greater. And that's something that we'll look at again in a later unit.